Welcome to Two Projects. In this video, we are going to explain the project, a novel hybrid model to predict dissolved oxygen for efficient water quality in intensive aquaculture. Introduction. With aquaculture playing a pivotal role in global food production, particularly in China, where it accounts for a significant portion of aquatic product output, ensuring water quality is crucial for sustaining healthy aquatic life and maximizing productivity. Dissolved oxygen, that is DO, serves as a vital indicator of water quality in aquaculture settings, directly impacting the growth and well being of aquatic organisms. Deviations from optimal DO levels can lead to detrimental effects such as disease outbreaks and economic losses. Traditional methods for predicting dissolved oxygen content often struggle with accuracy and speed due to the non-linear and dynamic nature of aquatic environments, posing challenges for effective aquaculture management. So, to address these challenges, this project proposes a novel hybrid model integrating the light gradient boosting machine and the bidirectional simple recurrent unit augmented with an attention mechanism. This approach aims to enhance prediction accuracy and speed while efficiently capturing complex aquatic dynamics. Objective of the project. So, as I mentioned earlier, the primary objective of the project is to improve the accuracy of dissolved oxygen prediction in intensive aquaculture environments. This will be achieved through the implementation of the proposed hybrid model light GBM plus by SRU plus attention, which combines light GBM for feature extraction, bidirectional simple RNN for model optimization, and attention for learning and weighing parameter updates. Another key objective is to conduct a comparative analysis between the proposed light GBM by SRU attention model and existing algorithms such as light GBM LSTM and light GBM GRU. This comparative assessment will help in identifying the best performing model in terms of prediction accuracy and efficiency. Through comparative analysis, the project seeks to evaluate the strengths and weaknesses of each model, considering factors such as mean square error, mean absolute error, and root mean square error. So, this analysis enables the selection of the most effective model for predicting DO levels in intensive aquaculture settings. Additionally, the project aims to showcase the importance of feature extraction in enhancing prediction accuracy. So, by utilizing light GBM for feature selection and extraction, the objective is to demonstrate how relevant features can significantly contribute to improving the performance of predictive models in intensive aquaculture settings. So, requirements needed to execute this project are software requirements. Software needed is Anaconda. Primary language used is Python. Front-end framework used is Flask. Backend framework used is Jupyter Notebook. Database used is SQLite 3. And front-end technologies used are HTML, CSS, JavaScript, and Bootstrap 4. Hardware requirements needed are operating system of Windows, processor of i5 and above, RAM of 8 GB and above, and hard disk of 25 GB and above. Now we'll discuss the working models of flow of work. So the first step is import and required packages. In this step, we import essential libraries such as NumPy, Pandas, sklearn, Matplotlib, and Keras. These packages are necessary for data manipulation, visualization, and building machine learning models. The second step is exploring the dataset. Here we analyze the dataset to understand its structure, features, and distribution. We check for any missing values or inconsistencies that may require pre-processing before model training. The third step is data processing. In this step, we handle null values and perform data pre-processing to clean and prepare the dataset for analysis. The next step is visualization using Matplotlib. So using Matplotlib, we visualize the data to gain insights and understand patterns. This includes plotting graphs to visualize the distribution and relationships between variables. The next one is feature extraction. Here we employ light GBM for feature extraction, selecting relevant features that have the most significant impact on the target variable. This helps improve model performance and efficiency by reducing dimensionality and focusing on important features. The next step is train and test split. In this step, we split the dataset into training and testing sets to evaluate the model's performance. The training set is used to train the model, while the testing set is used to assess its accuracy and generalization ability. The next step is training and building the model. Here we train and build the light GBM by SRU attention, that is combination of light GBM bidirectional simple RNN and attention model. So we will also train light GBM LSTM and light GBM GRU models using the training data. So light GBM is used for features extraction. These models incorporate different algorithms and techniques to predict dissolved oxygen levels accurately. And in the next step, as an extension to the project, we combine bidirectional LSTM, GRU, simple RNN, and attention mechanisms with features extracted from light GBM to create a more robust and accurate prediction model. And in the next step, as an extension again, we utilize the Flask framework to develop a front end for user testing. And we integrate SQLite for user authentication, allowing users to sign up and sign in before providing input features for prediction. So, after signing in, users input feature values which are pre processed to match the model's input format. And the trained model is then used to make predictions based on the provided features. The final prediction outcome is displayed through the front end, allowing users to visualize and interpret the predicted dissolved oxygen levels. Now we'll understand about the algorithms used. So the first algorithm built is Light GBM by SRU attention model. So this model integrates Light GBM for feature extraction, bidirectional simple recurrent unit for optimizing training features from both backward and forward positions, and attention mechanism for learning and weighing parameter updates. So Light GBM efficiently selects relevant features while BiSRU captures sequential dependencies in the data, and attention mechanism enhances the model's ability to focus on important information. This combination addresses the non-linear and dynamic nature of aquatic environments, making it suitable for predicting dissolved oxygen levels accurately in intensive aquaculture settings. The next algorithm built is Light GBM LSTM. So this model combines the light gradient boosting machine, that is LGBM algorithm, with long short-term memory, that is LSTM networks, for predicting dissolved oxygen levels in intensive aquaculture environments. Light GBM efficiently selects relevant features and reduces dimensionality, while LSTM captures sequential dependencies in the data, crucial for modeling time series like water quality parameters. This hybrid approach leverages the strengths of both algorithms, enhancing prediction accuracy and enabling effective modeling of complex temporal dynamics inherent in aquaculture systems. The next one is Light GBM GRU. So this model combines the light gradient boosting machine algorithm with the gated recurrent unit, that is GRU neural network. So Light GBM efficiently handles feature extraction and selection, prioritizing relevant features for dissolved oxygen prediction. And GRU, a type of recurrent neural network, captures temporal dependencies in the data, allowing the model to learn from sequential patterns and dynamics inherent in aquaculture environments. So, this combination offers improved prediction accuracy by leveraging Light GBM's feature selection capabilities and GRU's ability to capture temporal dependencies, making it suitable for accurately forecasting dissolved oxygen levels in intensive aquaculture settings. Now we'll see the comparison graphs. So this is the horizontal bar graph comparing MSc scores of different algorithms. In this graph on x-axis I have MSc scores and on y-axis I have algorithm names. MSc calculates the average of the squared differences between predicted and actual values, providing a measure of the overall variance or spread of errors. It penalizes larger errors more heavily due to the squaring operation. This is RMSE scores comparison graph. In this graph on x-axis I have RMSE scores and on y-axis I have algorithm names. RMSE is the square root of MSE and provides a measure of the standard deviation of prediction errors. It is in the same units as the target variable, making it easier to interpret compared to MSE. And this is MAE scores comparison graph. In this graph on x-axis I have MAE scores and on y-axis I have algorithm names. MAE computes the average of the absolute differences between predicted and actual values. Unlike MSC, it does not square the errors, offering a more straightforward interpretation of prediction accuracy. So, the algorithm which is best performing in all the performance metrics will be used for predictions. Execution of the project. To execute this project, first we need to open the code folder which contains the project source code files. So, this is dataset folder in which I have required dataset on which we'll train the models. This is static folder in which I have model files which contain algorithm information. These files will be loaded into the project code during runtime to utilize the trained models. This is also a model file. This is static folder. This folder consists of files related to CSS, JavaScript, and Bootstrap. This is templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, etc., which represent different pages of the website. This is app.py file. This .py file contains the information related to front-end logic. It includes coded in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML pages. This is Python main code file. This is water quality Jupyter source file. So this Jupyter source file contains a combination of code, graphs, and outputs all in one place. It allows users to write and execute code in individual cells, making it a popular choice for data science. And this is signup.db file. This file is the database file used to store user information. So now copy the path of the code folder from the address bar of the file explorer. I'm copying it. Open Anaconda prompt. So now use the command cd followed by a space and paste the copied path and hit the enter button. So this command is used to change the current directory to the code folder's path. Now compile the app.py file using the command python space app.py. I'm typing python space app.py and hit the enter button. So this command will execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, the Flask framework will host the application locally at the default address, localhost, and port unless configured differently. Now copy the local link provided by the framework. I'm copying it and paste it into any web browser. I prefer Chrome. After pasting it, hit the enter button. So the home page of the project has been displayed in the browser. This is the front end built using Flask framework. So here we can see a logon link, click on it. So if we are new users, we have to register first, fill in all these details and click on sign up button to register. If we already have an account, we can directly log in by clicking on this link. So as I already have an account, I'm clicking on this link. Here we have to provide a credentials, username and password and click on sign in button. So it has redirected us to the predictions page. Now we have to fill in all these parameters and click on predict button to get the predictions of dissolved oxygen. First we'll understand these parameters. The first one is pH. So pH measures water acidity or alkalinity on a scale of 0 to 14, influencing chemical reactions, nutrient availability and aquatic organism health. The next one is turbidity. Turbidity measures water clarity by quantifying suspended particles affecting light penetration, aquatic habitat quality, and overall ecosystem health. And the next one is conductivity. Reflecting ion concentration, conductivity measures water's electrical conductivity, indicating salinity, mineral content, and potential impacts on aquatic ecosystems and water quality. So now we'll fill in these parameters. pH would be 7.25. Turbidity is 4.5. Conductivity would be 342. Now click on predict button. So here we can see the result, that is dissolved oxygen level of water is 7.00 milligrams per liter. We'll try again, click on home link. We'll try giving another set of parameters. This time pH would be 6.92. Turbidity is 4.9 and conductivity would be 362. Now click on predict button. So here we can see the prediction, that is dissolved oxygen level of water is 7.009 milligrams per liter. So similarly, we can enter any set of parameters and can get the predictions of the dissolved oxygen level. Now click on logout. So the conclusion here is this project aimed to introduce a novel approach to predict water quality in intensive aquaculture settings, addressing the crucial need to maintain healthy water conditions for aquatic life, particularly in regions heavily reliant on aquatic food exports. So the proposed hybrid model Light GBM by SRU attention integrates Light GBM for feature selection, bidirectional simple RNN for optimizing training features, and attention for learning parameter updates. This model offers a comprehensive approach to predicting dissolved oxygen levels in aquaculture environments, leveraging the strengths of each component for improved accuracy. Additionally, variants such as Light GBM LSTM and Light GBM GRU were considered for comparative analysis in terms of prediction accuracy and efficiency. And an extension model ensemble combining bidirectional LSTM, GRU, simple RNN, and attention outperformed individual algorithms, demonstrating improved MSC error rates and highlighting the effectiveness of ensemble techniques in enhancing prediction accuracy. And integration of Flask framework with SQLite for user authentication provided a user-friendly interface for testing the models. Users could input data and receive predictions, facilitating practical application and usability. And the beneficiaries of this project include aquaculture industries, environmental agencies, and researchers. Accurate prediction of dissolved oxygen levels enables better management of water quality, promoting healthier aquatic environments and supporting sustainable aquaculture practices, ultimately benefiting both industry and environmental conservation efforts.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.